November 1, 1943, Empress Augusta Bay, Bougainville Island. For American light cruisers steam through Black Pacific waters. USS Montpelier leads USS Cleveland, USS Columbia, and USS Denver in column formation. Each warship carries 12 6-inch guns and the most advanced fire control radar ever mounted on a cruiser. Tonight, these Cleveland-class vessels will shatter Japan's mastery of night naval combat forever. The stakes are absolute. American Marines have just landed at Cape Torokina, and Japanese heavy cruisers race south from Rabaul to destroy the invasion fleet. Radar operator second-class Tommy Mitchell crouches over his Mark 8 fire control scope aboard USS Cleveland. The green sweep arm rotates through darkness, painting electronic pictures of ships that human eyes cannot see. At 2:27 in the morning, bright blips appear on his screen. Range, 28,000 yards. Bearing, 320 degrees relative. For large contacts and 6 smaller ones. The Japanese task force approaches exactly as intelligence predicted. Contact. Mitchell calls into his headset. Multiple surface targets. Bearing 320, range 28,000. In the Combat Information Center deep within Cleveland's armored hull, Lieutenant Commander James Parker studies the radar repeater display. The electronic blips move steadily southward at 22 knots. Parker calculates course and speed with mechanical precision. The Japanese formation consists of heavy cruisers Myoko and Haguro, light cruisers Sendai and Agano, plus 6 destroyers under Rear Admiral Sentaro Amori. Their mission: smash through American screening forces and annihilate the vulnerable transports anchored in Empress Augusta Bay. Parker reaches for the battle telephone. All stations, combat. We have multiple Japanese surface contacts bearing 320, range decreasing. Recommend general quarters. Throughout Cleveland, alarm bells shatter the tropical night. 850 sailors race to battle stations. In Turret 2, gunners mate First Class Robert Santos checks the loading mechanisms of his 6-inch Mark 16 guns. Each barrel can fire 10 rounds per minute with radar-directed accuracy. Santos has trained for this moment through countless Pacific battles. Tonight, American technology will prove itself against Japanese night fighting superiority. 24 miles northwest, aboard heavy cruiser Myoko, Captain Terahiko Miyazaki peers through powerful binoculars. His lookouts scan empty darkness for American muzzle flashes. Japanese doctrine depends on superior night vision, intensive training, and devastating long-lance torpedoes. Miyazaki's crew has drilled endlessly in night combat. They expect to close unseen, launch torpedo spreads, then finish survivors with 8-inch gunfire. Lookouts report no enemy contacts, announces Myoko's navigator. Miyazaki nods with satisfaction. American forces lack proper night fighting skills. Japanese superiority in darkness is absolute. His heavy cruisers carry 10 8-inch guns each, massive weapons that can smash enemy light cruisers at close range. The long lance torpedo extends to 24 miles with a 1,210-pound warhead. American torpedoes are inferior in every measure. But Miyazaki cannot see the invisible electronic eyes now tracking his every movement. Mark 8 fire control radar penetrates darkness with microwave precision. The system provides range accuracy of 15 yards plus 0.1% of distance. At current range, American gunfire solutions are calculated within 50 yards of perfect accuracy. Aboard USS Montpelier, Rear Admiral Aaron Stanton Merrill commands Task Force 39 from his flagship's bridge. Merrill has studied every Japanese night action since Pearl Harbor. He knows enemy tactics. Approach in darkness, launch mass torpedo attacks, then close for point-blank gunnery. American losses at Savo Island, Cape Esperance, and Guadalcanal followed this pattern. Tonight will be different. All ships, this is Merrill. The Admiral announces over TBS radio. Enemy formation consists of 4 cruisers and 6 destroyers. We will execute Plan Roger. Destroyers attack first. Cruisers hold fire until torpedoes run. Merrill's tactical innovation breaks from standard doctrine. Instead of engaging immediately, His cruisers will remain at long range while destroyers launch coordinated torpedo attacks. Radar provides perfect tracking information. American 5-inch guns with proximity fuses can engage targets beyond visual range. The Japanese advantage in night vision becomes meaningless against electronic detection. Captain Arleigh Burke commands Destroyer Squadron 23 from USS Charles Osborne. His 4 destroyers race ahead of the cruiser column: Charles Osborne, Dyson, Stanley, and Claxton. Burke has revolutionized destroyer tactics through aggressive leadership and superior seamanship. His sailors call themselves the Little Beavers, after their commander's tireless energy. All beavers, this is Burke. Execute torpedo attack on bearing 320. Launch when range closes to 10,000 yards. Burke's destroyers increase speed to 32 knots. Their Mark 15 torpedoes carry only 500-pound warheads compared to Japanese long lances, but American fire control provides unprecedented accuracy. Each destroyer mounts 5 torpedo tubes plus 5 5-inch dual-purpose guns. More importantly, they carry the latest Mark 14 fire control radar linked to Mark 37 directors. Japanese lookouts finally spot Burke's destroyers at 2:45 in the morning. Range has closed to 12,000 yards. Light cruiser Sendai immediately opens fire with 6-inch guns, followed by destroyers Shigure, Samidare, and Shiritsuyu. Orange muzzle flashes illuminate both forces as the first gunnery exchange begins. But American radar has been tracking Japanese movements for 18 minutes. Every ship position, course, and speed is plotted with electronic precision. When Burke's destroyers launch 40 Mark 15 torpedoes at 2:47, their targeting solutions are calculated by mechanical computers receiving continuous radar data. Aboard Myoko, Captain Miyazaki watches his screening destroyers engage the American attack force. He expects routine victory. Japanese destroyers are superior in night combat, armed with devastating long-lance torpedoes and rapid-firing guns. His heavy cruisers will sweep aside any surviving American vessels. Prepare for torpedo attack, Miyazaki orders. All tubes ready. Myoko carries 16 long-lance torpedoes in 4 quadruple mounts. Each torpedo weighs 3,070 pounds with a warhead of 1,210 pounds of explosive. Maximum range extends to 24 miles at 36 knots. No American torpedo matches Japanese long-lance performance in range, speed, or destructive power. But as Miyazaki prepares his attack, American radar operators observe every Japanese movement. Aboard Cleveland, radar operator Mitchell tracks individual ships with unprecedented clarity. His Mark 8 system penetrates darkness, smoke, and weather with microwave precision. Range measurements update every 2 seconds. Bearing accuracy extends to 0.1 degrees. Japanese cruisers turning to starboard, Mitchell reports. Range 24,000. Bearing 315, speed 22 knots. Lieutenant Commander Parker plots the enemy maneuver on his radar display. Japanese forces are attempting to close for torpedo attack. Their formation has become confused during the destroyer engagement. Heavy cruisers Myoko and Haguro have separated from light cruisers Sendai and Agano. Destroyer division integrity is breaking down under American pressure. At 2:50 in the morning, Rear Admiral Merrill orders his cruisers to open fire. For Cleveland-class vessels, turn their main batteries toward radar-designated targets. 48 6-inch guns train on bearing 315. Each turret receives firing solutions calculated by Mark 8 rangekeepers receiving continuous radar data. All batteries, commence firing, announces Cleveland's gunnery officer. 12 6-inch Mark 16 guns roar simultaneously. High explosive shells weighing 130 pounds streak across dark waters at 2,600 feet per second. Flight time to target, 37 seconds. American gunfire is directed by the most advanced fire control system in naval history. The first salvo from Task Force 39 creates a thunderous wall of sound. 48 heavy guns fire in unison, their muzzle flashes illuminating the entire formation. But unlike previous night actions, American gunfire is not directed by visual spotting or searchlight illumination. Electronic eyes guide every shell toward its target with mechanical precision. Japanese lookouts aboard Sendai see the American muzzle flashes 24,000 yards away. Captain Kishi orders immediate return fire with his light cruiser's 6-inch guns. But Sendai's optical fire control cannot match radar accuracy at such extreme range. Japanese shells fall short by 2,000 yards, their splashes invisible to American radar operators. Meanwhile, American shells approach their targets with calculated precision. The first shells from USS Montpelier strike Sendai amidships at 2:51. 6-inch high-explosive rounds penetrate the light cruiser's thin armor, detonating inside machinery spaces. Secondary explosions tear through Sendai's boiler rooms. The Japanese vessel slows immediately, trailing smoke and steam. Aboard Myoko, Captain Miyazaki watches in disbelief as American shells find their targets in total darkness. How can enemy gunfire achieve such accuracy without visual reference? Japanese night fighting doctrine assumes American forces cannot shoot effectively beyond visual range. Yet shells continue to impact with devastating precision. Return fire immediately, Miyazaki orders. All batteries, target the enemy muzzle flashes. Myoko's 10 8-inch guns swing toward the American formation. Each Type 3 shell weighs 277 pounds with enough explosive power to cripple any light cruiser. But Japanese fire control depends on optical rangefinding and visual spotting. At 24,000 yards in total darkness, accuracy becomes purely theoretical. The heavy cruiser's first salvo falls 3,000 yards short. Miyazaki's range estimate proves incorrect without electronic aids. His optical rangefinders cannot function effectively beyond 15,000 yards in darkness. Meanwhile, American radar continues to provide perfect targeting information every 2 seconds. Cleveland's second salvo arrives 38 seconds after her first. 12 6-inch shells bracket Sendai with devastating accuracy. 2 rounds penetrate the bridge structure, killing Captain Kishi and his entire command staff. 3 more shells tear through the engine room, destroying main steam lines. Sendai begins to list heavily to port as flooding spreads throughout her hull. USS Columbia joins the engagement with devastating effect. Her radar-directed gunfire targets destroyer Hatsuke's, which has become separated from the main Japanese formation. 12 6-inch shells impact the destroyer's hull in rapid succession. The small warship disintegrates under concentrated firepower, her magazine detonating in a brilliant orange fireball visible for 20 miles. Japanese destroyer divisions attempt to close for torpedo attack, but American 5-inch guns with proximity fuses create an impenetrable barrier. The new variable time fuse detonates automatically when shells approach their targets. Japanese destroyers face a wall of precisely timed airbursts that devastate their upper works and personnel. Commander Bernard Austin leads Destroyer Division 46 in support of the main engagement. His 4 destroyers, Spence, Thatcher, Converse, and Foote, steam on the disengaged side of the cruiser formation. Austin's mission involves preventing Japanese forces from breaking through to the vulnerable transport anchorage. At 2:58, Austin observes Japanese destroyer movements on his radar display. 3 enemy vessels are attempting to circle around the American formation. Their long lance torpedoes pose a deadly threat to the cruiser column. Austin orders his division to intercept at maximum speed. All ships, this is Austin. Come left to course 270, speed 30 knots. We will engage the Japanese destroyers attempting to penetrate our screen. Austin's destroyers race through dark waters toward their targets. Each vessel mounts 5 5-inch dual-purpose guns controlled by Mark 37 directors with Mark 12 radar. American destroyers possess superior fire control compared to their Japanese counterparts, though they lack the devastating long lance torpedo. Japanese destroyer Samudera launches 8 long lance torpedoes toward the American cruiser formation. Each torpedo runs at 40 knots with a range extending to 12 miles. The oxygen-fueled engines leave no visible wake in darkness. Long lance torpedoes represent Japan's most effective naval weapon, capable of sinking battleships with single hits. But American radar operators track the torpedo launch immediately. Electronic detection reveals the precise bearing and estimated time of weapon impact. Rear Admiral Merrill orders an emergency turn to port, presenting stern aspects to the incoming torpedo spread. All 4 Cleveland-class cruisers execute the maneuver simultaneously, their formation integrity maintained through precise navigation. The 8 long lance torpedoes pass harmlessly astern of the American formation. Their magnetic exploders fail to trigger against empty water. Japanese torpedo attacks, so devastating at Savo Island and other night actions, prove ineffective against radar-directed maneuvering. Aboard heavy cruiser Haguro, Captain Sugiura watches his force disintegrate under accurate American gunfire. Light cruiser Sendai is burning fiercely and falling behind the formation. Destroyer Hatsukaze has exploded and sunk. His own vessel has suffered minor damage from near misses. American fire control appears almost supernatural in its precision. How can they shoot so accurately in darkness? Sugiura asks his gunnery officer. Unknown, Captain. Perhaps they are using searchlights beyond our visual range. But no searchlight beam penetrates the tropical night. American accuracy derives from electronic systems beyond Japanese comprehension. Mark 8 fire control radar can track multiple targets simultaneously while calculating precise firing solutions. The technological gap has become insurmountable. At 3:05, USS Denver receives 3 8-inch shells from Myoko. The heavy cruiser has finally achieved accurate range estimation through successive salvos. Japanese shells strike Denver's forward superstructure, causing significant damage but no critical systems failure. Miraculously, all 3 enemy shells prove to be duds, their impact fuses failing to detonate. Denver's damage control teams immediately assess the situation. Lieutenant Jack Morrison leads repair parties to the forward damage area. His sailors discover that Japanese armor-piercing shells have punched clean holes through the light cruiser's plating without exploding. American damage control procedures prove superior to weapons design flaws in enemy ammunition. Damage control to bridge, Morrison reports. Forward superstructure damaged but seaworthy.
No fires, no flooding.
We can maintain full combat capability. Denver continues in formation, her 12 6-inch guns still operational. American cruiser design emphasizes survivability and damage control. Compartmentalization prevents single hits from disabling entire vessels. Cleveland-class cruisers prove remarkably resilient under combat conditions. Japanese forces attempt to disengage at 3:10 as their tactical situation deteriorates beyond recovery. Admiral Amori orders a general withdrawal toward Rabaul. His formation has suffered catastrophic losses. Light cruiser Sendai sinking, destroyer Hatsukaze destroyed, multiple vessels damaged. American radar-controlled gunfire has proven devastatingly effective. But Rear Admiral Merrill refuses to allow enemy escape. His Task Force 39 pursues the retreating Japanese column, maintaining radar contact throughout the withdrawal. American cruisers possess superior speed and endurance compared to battle-damaged enemy vessels. The pursuit continues for 2 hours across dark Pacific waters. Cleveland's radar operators track individual Japanese ships with electronic precision. Sendai has fallen far behind the main formation, her speed reduced to 8 knots by massive internal damage. The burning light cruiser presents an ideal target for concentrated gunfire. American shells continue to impact her hull every 30 seconds. At 3:25, Sendai's forward magazine detonates in a massive explosion visible for 30 miles. The Japanese light cruiser breaks apart and sinks immediately, taking 437 sailors to the bottom of Empress Augusta Bay. American radar-directed gunfire has achieved complete tactical success against a superior enemy force. The Battle of Empress Augusta Bay marks the end of Japanese night fighting supremacy. American radar technology has revolutionized naval combat, making enemy advantages in training and torpedo armament irrelevant. Electronic detection systems penetrate darkness with mechanical precision, guiding gunfire toward targets beyond visual range. But this technological revolution extends far beyond single battle outcomes. Cleveland-class and Baltimore-class cruisers represent a new generation of warships designed around radar fire control systems. Their role in the Pacific War involves 3 critical missions: anti-aircraft protection for fast carrier task forces, naval gunfire support for amphibious operations, and surface combat against remaining Japanese fleet units. The Fast Carrier Task Force represents the pinnacle of American naval power in the Pacific War. These massive formations center around Essex-class aircraft carriers supported by new Iowa-class fast battleships, Cleveland-class light cruisers, and Baltimore-class heavy cruisers. Radar-equipped cruisers provide the primary anti-aircraft screen protecting vulnerable carriers from Japanese air attack. Task Force 58 operates as the main striking force of Admiral Chester Nimitz's Pacific Fleet. During 1944, this formation includes 18 aircraft carriers, 8 fast battleships, 2 Alaska-class large cruisers, and numerous cruisers and destroyers. The entire force commands more firepower than any navy in human history. Lieutenant Commander David Walsh commands anti-aircraft battery control aboard USS Baltimore during carrier operations off the Marianas. His responsibility involves coordinating defensive fire from 8 5-inch dual-purpose guns, 48 40mm Bofors guns, and 24 20mm Oerlikon cannon. Baltimore's anti-aircraft armament exceeds that of most pre-war destroyers. All AA batteries, this is Walsh. He announces over the ship's general announcing system, Air Raid Warning Red. Multiple bogies inbound bearing 090, range 60 miles, and closing. Baltimore's SK Air Search Radar has detected a formation of 36 Japanese aircraft approaching from Guam. The enemy strike consists of 18 Mitsubishi A6M0 fighters, 12 Nakajima B5N torpedo bombers, and 6 Yokosuka D4Y dive bombers. Their mission involves penetrating the American carrier screen and sinking at least one fleet carrier. But Task Force 58 deploys defensive systems beyond Japanese comprehension. Radar picket destroyers provide early warning at ranges exceeding 100 miles. Combat air patrol fighters receive precise vectoring from carrier-based fighter direction officers. Anti-aircraft cruisers create overlapping fields of fire using proximity-fused ammunition and advanced fire control systems. Baltimore's Mark 37 fire control directors track incoming Japanese aircraft with electronic precision. Each 5-inch gun mount receives continuous target bearing, range, and altitude data from centralized computers. The new variable time fuse automatically detonates shells at optimal distances from their targets, creating deadly fragmentation patterns. At 3:38 in the afternoon, Japanese aircraft penetrate to within 12 miles of the carrier formation. Baltimore opens fire with her main anti-aircraft battery. 8 5-inch guns fire in rapid succession, their shells detonating among the enemy formation with devastating accuracy. 3 Japanese bombers disintegrate under direct hits. Radar-controlled gunfire proves far superior to visual tracking methods. American cruisers can engage aircraft at maximum gun range, creating multiple defensive layers before enemy planes approach their carriers. The technological advantage extends to ammunition design, with proximity fuses multiplying anti-aircraft effectiveness by factors of 3 to 5. Japanese pilots face defensive firepower beyond their previous experience. Task Force 58's coordinated anti-aircraft fire involves hundreds of guns directed by unified radar systems. Individual aircraft survival becomes nearly impossible against such concentrated opposition. The mission deteriorates into a massacre as American technology overwhelms Japanese training and courage. Ensign Hiroshi Tanaka pilots his Nakajima B5N torpedo bomber toward the American carrier formation. His aircraft carries a single Type 91 torpedo with an 800-pound warhead. Tanaka has trained extensively for this mission, practicing low-level approaches against maneuvering targets. His squadron represents Japan's most experienced naval aviators. But Tanaka faces defenses beyond his tactical calculations. American radar tracks his aircraft from 60 miles away. Combat air patrol fighters receive precise vectoring information to intercept his formation before reaching attack position. If he survives the fighter screen, radar-controlled anti-aircraft guns will engage his bomber with devastating accuracy. At 12 miles from the nearest carrier, Tanaka encounters the outer anti-aircraft zone. Heavy cruiser USS Boston opens fire with 9 8-inch guns loaded with variable time fused ammunition. Each shell detonates automatically when radar proximity sensors detect aircraft within lethal radius. The sky fills with precisely timed explosions creating walls of steel fragments. Tanaka's bomber suffers multiple hits from shell fragments. His port wing fuel tank explodes, and hydraulic fluid sprays across the cockpit. The aircraft becomes increasingly difficult to control as battle damage accumulates. Yet he continues toward the carrier formation, determined to complete his attack mission despite overwhelming odds. Baltimore's 40mm Bofors guns engage at 8 miles range. These Swedish-designed weapons fire explosive shells at 120 rounds per minute per barrel. Baltimore mounts 12 quadruple Bofors mounts, creating devastating close-range firepower. The guns are directed by Mark 51 directors with integrated radar systems. Target bearing 085, range decreasing rapidly, announces Baltimore's Bofors director-operator. All mounts commence firing. 48 Bofors guns open fire simultaneously. Their explosive shells create a solid wall of steel and flame across the bomber's approach path. Tanaka's aircraft disintegrates under concentrated fire, its torpedo detonating harmlessly in the Pacific. The pilot's sacrifice achieves nothing against American technological superiority. The Japanese air attack fails completely. All 36 aircraft are shot down by combat air patrol fighters or anti-aircraft fire. No American ship suffers significant damage. Task Force 58 continues its mission without interruption, launching additional airstrikes against Japanese bases throughout the Marianas. This defensive success repeats throughout the Pacific campaign. American radar-equipped cruisers provide impenetrable anti-aircraft screens for carrier task forces. Japanese aviation, once dominant in the Pacific War, faces technological opposition that transforms aerial combat into systematic slaughter. The Great Marianas Turkey Shoot exemplifies American anti-aircraft effectiveness. But cruiser missions extend beyond defensive operations. Baltimore-class heavy cruisers excel in shore bombardment operations, providing precise naval gunfire support for amphibious landings throughout the Pacific. Their 8-inch guns with advanced fire control systems can engage targets up to 17 miles inland with devastating accuracy. USS Pittsburgh approaches Iwo Jima on February 19, 1945, as part of the pre-invasion bombardment force. Her mission involves destroying Japanese defensive positions overlooking the planned landing beaches. Enemy fortifications have been constructed with exceptional skill, taking advantage of the island's volcanic terrain and natural caves. Captain John Gingrich studies aerial reconnaissance photographs on Pittsburgh's bridge. Japanese defenses on Iwo Jima represent the most formidable fortifications encountered in the Pacific War. Enemy engineers have created an elaborate network of bunkers, tunnels, and artillery positions designed to inflict maximum casualties on American assault forces. Gunnery officer to bridge, announces Lieutenant Commander Robert Hayes. Main battery ready for shore bombardment. We have target assignments for 6 major defensive positions. Pittsburgh's 9 8-inch Mark 15 guns represent the most advanced naval artillery in the world. Each turret contains 3 individually sleeved barrels controlled by Mark 34 directors with Mark 8 radar. The fire control system can engage multiple targets simultaneously while maintaining pinpoint accuracy at maximum range. Target number 1 consists of a Japanese coastal defense battery mounting 4 6-inch guns in reinforced concrete casemates. The position overlooks Red Beach 1, where the 4th Marine Division will land at 0900 hours. Eliminating this battery is essential for landing force survival. Pittsburgh's fire control radar locks onto the target coordinates provided by aerial reconnaissance. Mark 8 microwave systems can distinguish individual buildings and fortifications despite their camouflaged construction. Range to target, 14,200 yards. Bearing, 047 degrees true. Main battery, target coastal defense battery. Bearing 047. Range 14200. Load armor piercing. Stand by to commence firing. Each 8-inch gun loads a Mark 19 armor-piercing shell weighing 335 pounds. These projectiles can penetrate up to 13 inches of steel armor or destroy heavily reinforced concrete fortifications. Pittsburgh carries 1,200 rounds of 8-inch ammunition for extended bombardment operations. At 0730, Pittsburgh opens fire on her assigned targets. 9 8-inch guns roar in sequence, their shells streaking across 13 miles of Pacific water. Flight time to target, 28 seconds. American fire control systems calculate precise impact points despite the extreme range and challenging target characteristics. The first salvo from Pittsburgh impacts directly on the Japanese coastal battery. Armor-piercing shells penetrate concrete casemates and detonate inside the defensive positions. Secondary explosions indicate ammunition storage areas have been destroyed. The enemy battery ceases all activity after receiving 12 direct hits in 90 seconds. Japanese defenders on Iwo Jima have never experienced such accurate naval gunfire. American 8-inch shells land precisely on target coordinates despite the extreme range. Radar fire control eliminates the traditional problems of range estimation and target location that have limited naval bombardment effectiveness throughout history. Major General Tadamaki Kurabayashi commands Japanese forces on Iwo Jima from his headquarters deep underground. His defensive strategy depends on surviving the preliminary bombardment and inflicting maximum casualties when American forces attempt to land. But American naval gunfire proves devastatingly accurate, systematically destroying prepared positions. Report from coastal defense sectors. Kurabayashi demands. Battery positions under intense bombardment, replies his operations officer. American gunfire appears directed by aerial spotting. Our camouflaged positions are being targeted with precision. But American accuracy derives from radar systems, not aerial observation. Mark 8 fire control can distinguish individual targets through camouflage and deception measures. Electronic detection penetrates Japanese defensive preparations with mechanical precision, guiding shells toward their targets regardless of concealment efforts. USS Baltimore joins the bombardment with devastating effect. Her fire control radar identifies a Japanese artillery position housing 4 150mm howitzers. These weapons threaten the entire landing operation, capable of delivering devastating fire against assault craft approaching the beach. Baltimore's gunnery officer calculates the firing solution using radar data and ballistic computers. Range, 16,800 yards. Target elevation, 340 feet above sea level. Wind speed, 12 knots from the northeast. All variables enter the mechanical calculation systems automatically. Main battery, commence firing for effect. 9 8-inch shells impact the Japanese artillery position within a 50-yard circle. High explosive projectiles detonate among the enemy guns, destroying their mechanisms and killing trained crews. The howitzer battery ceases firing permanently after absorbing 36 direct hits in 4 minutes. This systematic destruction continues throughout the pre-invasion bombardment. American cruisers engage every identified Japanese position with radar-directed precision. Shore fire control parties coordinate target assignments to maximize destructive effect. The bombardment represents the most intensive naval gunfire preparation in Pacific War history. Flight Lieutenant Saburo Kitajima observes the American bombardment from his concealed observation post on Mount Suribachi. He has served as an artillery spotter throughout the Pacific Campaign, directing defensive fire against numerous American landings. But the bombardment of Iwo Jima exceeds anything in his previous experience. American shells land with mechanical precision, targeting individual bunkers and gun positions. Enemy fire control appears guided by detailed intelligence about Japanese defensive preparations. Kitajima realizes that traditional concealment methods prove ineffective against American detection capabilities. American gunfire is destroying our prepared positions systematically, he reports to headquarters. Their accuracy suggests advanced target location methods. Kitajima cannot comprehend the technological systems directing American naval gunfire. Radar penetrates camouflage and concealment with electronic precision. Fire control computers calculate ballistic solutions automatically. The entire system operates beyond Japanese technological capabilities or tactical understanding. As the bombardment intensifies, Kitajima observes American cruisers maneuvering offshore. These vessels appear far larger than previous light cruisers encountered in earlier battles. Their gunfire possesses devastating accuracy at extreme ranges. The ships represent technological advancement that surpasses Japanese naval development. Baltimore-class heavy cruisers embody American industrial and technological superiority. Each vessel requires 14,000 tons of steel, sophisticated radar systems, advanced fire control computers, and precision manufacturing techniques. Their construction represents capabilities beyond any other naval power in 1945. The pre-invasion bombardment of Iwo Jima demonstrates American naval supremacy in its most devastating form. Radar-equipped cruisers systematically destroy Japanese defensive positions with unprecedented accuracy. Shore bombardment evolves from area denial to precision target destruction through technological advancement. But even as American cruisers dominate surface combat and shore bombardment missions, they face new challenges from Japanese desperation tactics. Kamikaze attacks represent Japan's final attempt to achieve tactical success against overwhelming American technological superiority. These suicide missions target American aircraft carriers and their protecting cruiser screens. Task Force 58 operates off Okinawa during April 1945, supporting the largest amphibious operation in Pacific War history. The carrier formation faces continuous kamikaze attacks as Japanese aviation commits its remaining aircraft to suicide missions. American anti-aircraft cruisers must defend the task force against unprecedented aerial threats. USS Cleveland steams in the outer anti-aircraft screen of Task Group 58.3. Her mission involves intercepting Japanese kamikaze aircraft before they can approach the vulnerable aircraft carriers. Cleveland's radar systems detect incoming threats at maximum range, allowing coordinated defensive responses. At 0615 on April 6, Cleveland's SK air search radar detects a massive Japanese air formation approaching from the northwest. Range: 85 miles and closing at 200 knots. The formation consists of 183 kamikaze aircraft plus conventional escorts. Their target: Task Force 58. General Quarters, all hands to battle stations, announces Cleveland's commanding officer over the ship's general announcing system. This is not a drill. Multiple air contacts approaching from bearing 320. Cleveland's crew races to battle stations with practiced efficiency. Gunner's mate Second Class Antonio Rossi reaches his 40mm Bofors mount in 43 seconds. His quad mount represents one of 12 such weapons aboard the light cruiser. Each gun fires 120 rounds per minute with devastating effectiveness against aircraft. The incoming Japanese formation represents Kikusui No. 1, the first of 10 massed kamikaze attacks planned against American forces at Okinawa. Admiral Mato Mugaki commands the desperate operation from his headquarters on Kyushu. His mission involves destroying enough American carriers to halt the Okinawa invasion. Japanese pilots flying in Kikusui-1 have received minimal training compared to pre-war aviators. Many possess fewer than 100 hours of flight experience. Their aircraft range from modern fighters to obsolete training planes converted for suicide missions. But determination compensates for technological limitations. Ensign Kenji Nakamura pilots his Mitsubishi A6M0 toward the American task force. His aircraft carries a 500-pound bomb plus full fuel tanks, transforming the fighter into a guided missile. Nakamura has volunteered for this mission, believing his sacrifice will save Japan from defeat. At 60 miles from the American formation, Nakamura encounters the outer fighter screen. F-6F Hellcats from USS Essex intercept the Japanese formation with devastating results. American fighters possess superior performance, experienced pilots, and radar-guided interception systems. The aerial battle becomes systematically one-sided. But some Japanese aircraft penetrate the combat air patrol through numerical superiority and suicidal determination. At 30 miles from Task Force 58, surviving kamikaze aircraft face the concentrated anti-aircraft fire of radar-equipped cruisers and destroyers. This represents the most intensive defensive firepower in naval history. Cleveland opens fire at maximum range with her 5-inch dual-purpose guns. 12 barrels engage multiple targets simultaneously, their variable-time fused shells detonating automatically when proximity sensors detect aircraft within lethal range. The sky fills with precisely timed explosions creating walls of steel fragments. Multiple targets bearing 320, range decreasing rapidly, announces Cleveland's air defense officer. All batteries commence firing. 48 40mm Bofors guns join the engagement, followed by 24 20mm Oerlikon cannon. Cleveland's total anti-aircraft firepower exceeds most pre-war destroyers. Radar directors guide every weapon system toward its targets with electronic precision. Nakamura's Zero suffers multiple hits from American anti-aircraft fire. Shell fragments puncture his fuel tanks, and hydraulic fluid sprays across the cockpit. The aircraft becomes increasingly difficult to control as battle damage accumulates. Yet he continues toward the carrier formation, determined to complete his mission despite overwhelming defensive fire. At 8 miles from the nearest carrier, Nakamura faces the inner defensive zone manned by Baltimore-class heavy cruisers. USS Boston engages with 8 8-inch guns firing variable-time fused shells. Each projectile weighs 270 pounds and detonates automatically when radar sensors detect aircraft within killing range. Air target bearing 085, elevation angle 20 degrees. Reports Boston's Mark 37 fire control director. All batteries engage. Boston's coordinated anti-aircraft fire creates an impenetrable barrier across the kamikaze approach path. 8-inch shells detonate in perfect timing, their fragmentation patterns calculated to destroy any aircraft within a 1,000-yard radius. Nakamura's Zero disintegrates under direct hits, its bomb exploding harmlessly over empty ocean. The Kikusui-1 attack achieves minimal success against American defenses. Only 14 Japanese aircraft penetrate to attack positions out of 183 launched. American radar-directed anti-aircraft fire destroys the remainder with mechanical efficiency. Task Force 58 suffers minor damage to 3 destroyers but continues operations without interruption. This defensive success repeats throughout the Okinawa campaign. American anti-aircraft cruisers prove devastatingly effective against kamikaze attacks through technological superiority and coordinated fire control. Japanese suicide tactics, desperate though they are, cannot overcome radar-guided defensive systems. But individual kamikaze attacks occasionally achieve tactical success through determination and luck. USS Birmingham experiences the reality of Japanese desperation during operations off Mindoro in December 1944. Her crew learns that technological superiority cannot guarantee absolute protection against suicidal enemies. Birmingham steams in formation with Task Group 77.4, supporting amphibious landings in the central Philippines. Her mission involves providing anti-aircraft protection for escort carriers conducting close air support missions. The task group operates within range of Japanese airfields on Luzon, creating constant threat of air attack. At 13:45 on December 13th, Birmingham's air search radar detects a single Japanese aircraft approaching from the northeast. The contact appears to be a damaged bomber attempting to return to base. Standing orders require engagement of all unidentified aircraft within 20 miles of the formation. Single air contact bearing 045, range 18 miles. Reports Birmingham's Combat Information Center. Contact appears to be damaged enemy bomber. Lieutenant Commander Frank Morrison commands Birmingham's anti-aircraft battery from his position in sky control. His responsibility involves coordinating defensive fire from 12 5-inch guns, 48 40mm Bofors, and 24 20mm Oerlikon cannon. The approaching aircraft presents a routine interception target. But the Japanese bomber is actually a Mitsubishi G4M Betty converted for kamikaze attack. Flight Petty Officer First Class Yoshioseki pilots the aircraft toward the American formation with single-minded determination. His aircraft carries a 1,600-pound bomb plus full fuel tanks, creating a devastating guided weapon. Seki approaches Birmingham at low altitude, using cloud cover to mask his final attack run. His tactical training emphasized the importance of surprise in kamikaze attacks. American anti-aircraft fire proves devastatingly effective against aircraft detected at long range, but last-minute attacks can achieve success through shock and speed. Birmingham's 5-inch guns engage the approaching aircraft at 12 miles range. Variable time fused shells detonate around the Betty with precision timing, but the aircraft continues its approach despite battle damage. Saki's determination overcomes physical wounds and mechanical failures as his bomber races toward its target. Incoming bogey has penetrated 5-inch envelope, Morrison announces. All close-range batteries commence firing. 48 Bofors guns open fire simultaneously, their explosive shells creating a wall of steel across the Betty's flight path. 24 Oerlikon cannon join the defensive barrage. Birmingham's combined anti-aircraft firepower should destroy any attacking aircraft within 5 miles of the ship. But Saki's bomber survives the defensive fire through determination and tactical skill. The aircraft approaches Birmingham's port side at mast height, its engines trailing smoke and flame. At the last moment, Saki banks toward the light cruiser's superstructure, aiming for the bridge area where maximum casualties can be inflicted. The Betty crashes into Birmingham's forward superstructure at 13:52. Its bomb and fuel tanks detonate simultaneously, creating a massive fireball that engulfs the entire forward section of the ship. The explosion kills 239 sailors instantly and wounds 408 more. Birmingham's combat effectiveness is destroyed in seconds. Fire control parties throughout the ship respond to the catastrophic damage with trained efficiency. Lieutenant Robert Patterson leads damage control efforts in the forward section despite suffering severe burns and smoke inhalation. His sailors battle flames that threaten to spread throughout the vessel. Damage control to all stations, Patterson reports over the battle telephone circuit. Major fire forward, multiple casualties. We need all available firefighting equipment forward immediately. Birmingham's crew demonstrates the effectiveness of American damage control training and ship design. Despite catastrophic damage, the light cruiser remains afloat and operational. Compartmentalization prevents progressive flooding, while trained damage control parties contain the fires before they reach critical systems. The kamikaze attack on Birmingham illustrates both the limitations and strengths of American technological superiority. Radar-directed anti-aircraft fire cannot guarantee absolute protection against determined suicide attacks. But superior damage control and ship construction ensure survival even after successful kamikaze hits. Birmingham limps back to Pearl Harbor for extensive repairs lasting 6 months. Her survival demonstrates Cleveland-class structural integrity and damage control effectiveness. American shipbuilding techniques emphasize redundancy and survivability, allowing vessels to absorb tremendous punishment while remaining operational. As the Pacific War progresses toward its conclusion, American cruisers demonstrate technological dominance across all mission areas. Their radar-controlled gunfire revolutionizes naval combat, making traditional Japanese tactics obsolete. Anti-aircraft protection for carrier task forces proves devastatingly effective against kamikaze attacks. Shore bombardment operations systematically destroy enemy defensive positions with unprecedented accuracy. But perhaps the most significant impact involves the psychological effect on enemy forces. Japanese sailors and aviators face technological systems beyond their comprehension. American radar penetrates darkness and weather with electronic precision. Fire control computers calculate ballistic solutions automatically. Anti-aircraft guns engage targets beyond visual range with mechanical accuracy. Captain Yoshiro Sugimoto commands heavy cruiser tone during her final combat mission in July 1945. His vessel represents one of the last operational units of the Imperial Japanese Navy, hidden in Kure Harbor to avoid American air attacks. Sugimoto has witnessed the systematic destruction of Japanese naval power through overwhelming American technological superiority. American radar systems have made our traditional tactics useless, Sugimoto confides to his executive officer. They can see us in darkness and engage at ranges beyond our capability. Tone carries 8 8-inch guns and 12 long lance torpedoes, weapons that dominated Pacific combat during early war years. But against American radar-equipped cruisers, these systems prove inadequate. Japanese optical fire control cannot match electronic precision. Long lance torpedoes become irrelevant when enemies detect their launch immediately. On July 24, American carrier aircraft discover tone anchored at Kure. The heavy cruiser attempts to defend herself with anti-aircraft fire, but her obsolete fire control systems prove ineffective against coordinated air attack. Tone suffers devastating damage and capsizes at her moorings, representing the final destruction of Japanese cruiser power. The technological revolution exemplified by Cleveland-class and Baltimore-class cruisers extends far beyond their specific capabilities. These vessels represent American industrial capacity, technological innovation, and operational doctrine that transforms naval warfare fundamentally. Their success makes traditional Japanese advantages obsolete while establishing new standards for naval combat. Admiral William Halsey observes the evolution of naval warfare from his flagship USS New Jersey during operations against the Japanese home islands. Third Fleet operations in summer 1945 demonstrate complete American dominance across all aspects of naval combat. Japanese resistance has become token despite desperate sacrifice and tactical innovation. The radar-equipped cruiser has revolutionized naval warfare, Halsey notes in his personal diary. Night fighting, anti-aircraft defense, and shore bombardment have all been transformed by electronic systems.
El 6 observatium provas propatic.
Post-war naval development emphasizes radar integration, automated fire control, and electronic warfare capabilities. The principles established by World War II cruiser design continue to influence warship construction into the 21st century. Cleveland-class production totals 27 completed vessels, making them the most numerous cruiser class in naval history. Baltimore-class construction reaches 14 completed ships plus 3 Oregon City subclass vessels. Together, these cruiser classes represent the largest naval construction program in American history. American industrial capacity enables this massive production effort while simultaneously building aircraft carriers, battleships, destroyers, submarines, and amphibious vessels. No other nation possesses the manufacturing capability to sustain such comprehensive naval expansion. Industrial superiority proves as decisive as technological advancement. The human cost of this technological revolution extends to both sides of the Pacific conflict. American sailors benefit from superior equipment, training, and support systems. Japanese forces face increasingly hopeless odds against overwhelming technological and industrial advantages. Yet both sides demonstrate courage, skill, and dedication throughout the extended campaign. Radar operator second-class Tommy Mitchell survives the war aboard USS Cleveland, participating in every major Pacific operation from Empress Augusta Bay to the occupation of Japan. His experiences with radar fire control represent the transformation of naval warfare through electronic systems. Traditional seamanship skills combine with technological innovation to create unprecedented combat effectiveness. "We could see them before they could see us," Mitchell recalls years later. That changed everything about naval combat. Flight Lieutenant Saburo Kitajima also survives the war, captured on Iwo Jima after the American landing. His observations of radar-directed naval gunfire provide insight into Japanese perspectives on American technological superiority. Enemy capabilities exceeded Japanese understanding and defensive preparations. American naval gunfire was devastatingly accurate, Kitajima testifies during post-war interviews. Their shells landed precisely on target despite extreme range and concealment efforts. These individual experiences reflect the broader transformation of naval warfare during the Pacific Campaign. Radar technology enables unprecedented accuracy in gunnery, anti-aircraft defense, and tactical coordination. American cruisers become the primary beneficiaries of this technological revolution, their capabilities enhanced far beyond pre-war specifications. The strategic impact of radar-equipped cruisers extends throughout American Pacific strategy. Fast carrier task force operations become feasible through effective anti-aircraft protection. Amphibious landings succeed due to precise naval gunfire support. Surface combat victories eliminate remaining Japanese fleet units. American naval dominance becomes absolute through technological superiority. Japanese naval aviation suffers catastrophic losses against radar-directed anti-aircraft fire. Kamikaze attacks achieve limited tactical success despite suicidal determination. Traditional surface combat tactics prove obsolete against electronic fire control systems. The Imperial Japanese Navy ceases to exist as an effective fighting force by summer 1945. Shore bombardment operations systematically destroy Japanese defensive positions throughout the Pacific Campaign. American 8-inch guns with radar fire control can engage targets beyond visual range with pinpoint accuracy. Fortified positions that would have required prolonged siege warfare are neutralized through technological superiority. The psychological impact on Japanese forces proves equally devastating. American technological capabilities exceed Japanese understanding and defensive preparations. Electronic warfare systems operate beyond enemy comprehension. Traditional Japanese advantages in training, determination, and tactical skill become irrelevant against overwhelming technological superiority. American industrial capacity supports this technological revolution through massive production programs. Cleveland-class and Baltimore-class cruisers represent standardized designs that maximize manufacturing efficiency. Identical radar systems, fire control computers, and weapon systems simplify training, maintenance, and logistical support. British naval observers study American cruiser operations with professional interest and growing admiration. Royal Navy vessels lack the sophisticated radar fire control systems that make American ships so effective. British anti-aircraft guns rely primarily on visual tracking and manual calculation. Shore bombardment operations use optical rangefinding with limited accuracy. American radar fire control represents a quantum leap in naval gunnery, reports Captain James Henderson after observing Cleveland operations off Saipan. Their accuracy exceeds anything in Royal Navy experience. British naval development incorporates American technological advances through Lend-Lease programs and technical cooperation. Post-war Royal Navy construction emphasizes radar integration and automated fire control systems. American influence on British naval doctrine continues through the Cold War era. Soviet naval observers also study American cruiser capabilities through intelligence reports and captured equipment. Red Navy development during the post-war period emphasizes missile systems and electronic warfare capabilities. The lessons of radar-controlled naval gunnery influenced Soviet warship design for decades. German naval intelligence analyzes American cruiser technology through intercepted communications and combat reports. Kriegsmarine officers recognize the revolutionary nature of radar fire control systems. But German industrial capacity cannot match American production programs even with captured technology and scientific expertise. The technological gap between American and Axis naval forces becomes insurmountable by 1944. Radar systems, proximity fuses, automated fire control, and advanced damage control represent cumulative advantages that multiply combat effectiveness. Individual Japanese courage and skill cannot overcome systematic technological inferiority. Cleveland-class and Baltimore-class cruisers embody this technological revolution in their most advanced form. Their radar-controlled gunfire dominates surface combat and shore bombardment missions. Anti-aircraft protection for carrier task forces proves devastatingly effective against Japanese aviation. The vessels represent American naval supremacy at its technological peak. Post-war analysis reveals the comprehensive nature of American technological advantages. Radar fire control systems achieve accuracy improvements of 300% over optical methods. Proximity fuses increase anti-aircraft effectiveness by 400%. Damage control techniques reduce casualty rates by 60% compared to enemy vessels. These technological advantages compound through training, doctrine, and industrial support. American sailors receive comprehensive technical education in radar operation and maintenance. Fire control procedures emphasize electronic systems over visual methods. Industrial capacity provides replacement equipment and continuous upgrades. Japanese naval development cannot match American technological progress despite desperate efforts and resource allocation. Radar systems remain primitive and unreliable. Fire control computers are unavailable for most vessels. Industrial capacity proves inadequate for mass production of advanced equipment. The human dimension of this technological revolution involves millions of sailors, officers, and industrial workers. American success depends on comprehensive training programs, technical education, and industrial mobilization. Japanese forces demonstrate extraordinary courage and skill despite technological disadvantages. Individual heroism occurs on both sides throughout the Pacific Campaign. American sailors display professional competence and technological expertise under extreme combat conditions. Japanese forces demonstrate suicidal determination and tactical innovation against overwhelming odds. Both navies exemplify the highest traditions of naval service. But technological superiority ultimately proves decisive in naval warfare. Radar-equipped American cruisers achieve tactical dominance across all mission areas. Japanese forces face increasingly hopeless odds despite individual sacrifice and organizational effectiveness. The Pacific War demonstrates the revolutionary impact of electronic systems on military affairs. Cleveland-class and Baltimore-class cruisers continue serving in American and Allied navies through the Cold War era. Their radar fire control systems are upgraded with improved electronics and automated features. Many vessels receive guided missile armaments while retaining their original gun batteries. The basic design principles established during World War II remain relevant through decades of technological evolution. The legacy of radar-controlled naval gunnery extends into modern naval warfare. Contemporary warships emphasize electronic systems, automated fire control, and integrated battle management. The principles demonstrated by World War II cruisers continue influencing naval development in the 21st century. American naval supremacy achieved during the Pacific War establishes patterns that persist through subsequent conflicts. Technological superiority, industrial capacity, and comprehensive training programs create advantages that prove sustainable over time. The lessons of radar-controlled cruiser operations influence naval doctrine for generations. The transformation of naval warfare through radar technology represents one of the most significant military developments of the 20th century. Electronic systems enable unprecedented accuracy in gunnery while revolutionizing anti-aircraft defense and tactical coordination. American cruisers become the primary beneficiaries of this technological revolution. Japanese naval forces face technological challenges that exceed their industrial and scientific capabilities. Despite extraordinary courage and tactical innovation, enemy forces cannot overcome systematic American advantages in radar systems, fire control computers, and manufacturing capacity. The Imperial Japanese Navy suffers comprehensive defeat through technological inferiority. Individual battles demonstrate the decisive nature of technological superiority in modern warfare. Empress Augusta Bay, Philippine Sea, Leyte Gulf, and Okinawa operations showcase American radar advantages across all aspects of naval combat. Traditional Japanese strengths in night fighting, torpedo attacks, and aviation become irrelevant against electronic systems. The strategic implications of radar-controlled naval warfare extend throughout military planning and international relations. American technological superiority establishes naval dominance that influences global politics for decades. Electronic systems become essential for military effectiveness while industrial capacity determines national power. Cleveland-class and Baltimore-class cruisers represent the technological pinnacle of World War II naval development. Their radar fire control systems revolutionize gunnery accuracy while providing unprecedented anti-aircraft protection. Shore bombardment operations achieve precision that transforms amphibious warfare tactics. These vessels embody American naval supremacy through technological innovation. The human cost of technological warfare includes both American and Japanese casualties throughout the Pacific Campaign. Superior American equipment and training reduce casualty rates while improving mission effectiveness. Japanese forces suffer disproportionate losses despite individual heroism and tactical skill. Technology amplifies the consequences of industrial and scientific advantages. Post-war naval development continues emphasizing radar integration and electronic warfare capabilities. American cruiser designs influence warship construction worldwide while establishing doctrinal principles that remain relevant. The technological revolution initiated during World War II accelerates through subsequent decades of military innovation. Contemporary naval forces rely on electronic systems that trace their origins to World War II radar fire control development. Computer-aided targeting, automated weapon systems, and integrated battle management represent evolutionary advances from technologies first deployed on Cleveland-class and Baltimore-class cruisers. The fundamental principles remain unchanged despite technological sophistication. The legacy of radar-controlled naval gunnery demonstrates the revolutionary impact of electronic systems on military affairs. American cruisers achieved tactical dominance through technological superiority that made traditional naval combat obsolete. These lessons continue influencing military development and strategic planning in modern warfare. American industrial capacity enabled the technological revolution that transformed naval combat during the Pacific War. Mass production of sophisticated radar systems, fire control computers, and precision weaponry required manufacturing capabilities that exceeded any other nation. Industrial superiority proved as decisive as technological innovation in achieving naval dominance. The comprehensive nature of American advantages in radar technology, manufacturing capacity, and human resources created cumulative effects that proved insurmountable for Japanese forces. Individual technological innovations combined through systematic application to achieve revolutionary improvements in combat effectiveness. Cleveland-class and Baltimore-class cruisers represent this technological integration at its most successful. Japanese recognition of American technological superiority appears throughout captured documents and post-war testimony. Enemy forces acknowledged the decisive nature of radar fire control while struggling to develop countermeasures with limited industrial resources. The technological gap widened throughout the Pacific Campaign despite desperate Japanese efforts to close it. The strategic implications of technological warfare continue influencing international relations and military planning. Nations that achieve advantages in electronic systems, manufacturing capacity, and scientific research gain decisive military superiority. The lessons of World War II naval combat remain relevant for contemporary strategic planning. Cleveland-class and Baltimore-class cruisers achieved tactical dominance through radar-controlled gunfire that revolutionized naval warfare. Their success demonstrates the decisive impact of technological innovation on military effectiveness. These vessels represent American naval supremacy at its technological and operational peak during World War II. The transformation of naval combat through electronic systems establishes patterns that continue influencing military development. Radar technology enables unprecedented accuracy in gunnery while providing revolutionary improvements in anti-aircraft defense. American cruisers become the primary beneficiaries of this technological advancement. Individual heroism and professional competence characterize both American and Japanese naval forces throughout the Pacific Campaign. Superior American technology amplifies the effectiveness of training and courage while reducing casualty rates under combat conditions. Japanese forces demonstrate extraordinary sacrifice despite facing overwhelming technological disadvantages. The historical significance of radar-controlled naval warfare extends beyond specific battles or technological achievements. Electronic systems fundamentally alter the nature of military conflict while establishing new requirements for industrial capacity and scientific research. The Pacific War demonstrates these changes at their most dramatic. American naval supremacy achieved through technological innovation creates strategic advantages that influence global politics for decades. The principles established by radar-equipped cruisers continue affecting naval doctrine and warship design. Contemporary military forces trace their electronic warfare capabilities to World War II technological developments. The legacy of Cleveland-class and Baltimore-class cruisers represents the successful integration of technological innovation, industrial capacity, and professional competence. Their radar fire control systems revolutionized naval gunnery while establishing American dominance across all aspects of naval combat. These achievements demonstrate the decisive nature of technological superiority in modern warfare. Japan's stunned recognition of American radar cruiser capabilities marks a turning point in Pacific naval warfare. Electronic systems penetrate traditional Japanese advantages in night fighting, torpedo attacks, and aviation operations. The technological revolution initiated by American cruiser development transforms military affairs comprehensively. The comprehensive defeat of Japanese naval forces through American technological superiority establishes lessons that remain relevant for contemporary military planning. Electronic warfare capabilities, industrial capacity, and scientific research determine national power while influencing international relations. The Pacific War demonstrates these principles at their most fundamental level. Cleveland-class and Baltimore-class cruisers achieve unprecedented tactical effectiveness through radar-controlled systems that make traditional naval combat obsolete. Their success represents the triumph of American technological innovation over Japanese tactical skill and individual courage. The revolution in naval warfare proves both decisive and permanent in its strategic implications.